Swayam Prabha. Digital India. Educated India.
Welcome to Module E, Lecture 12. In this lecture also, we shall continue our discussion about operational analysis of signalized intersection. In Lecture 11, we discussed primarily about step 6, how to determine the capacity and volume to capacity ratio. Then step 7, determine delay. 8, how to determine level of service based on the control delay, and then we started our discussion and a few concepts also I explained in relation to queue storage ratio calculation. Now, in previous lecture we talked about NF, number of stopped vehicles, and also TF, the clearance time for clearing those or time required to clear those vehicles. Now, back of queue size represents the average back of queue size for the analysis period. So, what we considered there so far, NF and TF, it is only one part of it. There are more considerations while we are calculating the back of queue size. Now, back of queue size is based on those vehicles which arrive at the intersection during the analysis period, and of course, it also includes the vehicles that are still in the queue after the analysis period ends, because still all the vehicles which have arrived the intersection during the analysis period are cleared, we have to continue the process. So, actually if you see the back of the queue size for a given lane group is actually summation of Q1, Q2, Q3. What are the Q1, Q2, Q3? They are maybe the first term of the back of the queue size, second term of the back of the queue size, and third term of the back of the queue size respectively. So, Q is actual back of the queue size is sum over first term, second term, and the third term. Now, coming to the first term, that is actually what we have discussed in the previous lecture. This accounts for Q caused by signal cycling through its phase sequence. So, Q1 is straightway equal to NF, number of stopped vehicles, and you remember our discussion in the previous lecture that how to calculate this NF. Graphically I have shown you also what NF means, what is the interpretation of this one. So, Q1 component, the first term is clear to us. Now, the second term also is known to you. The second term includes actually two Q components. One, effect of random cycle by cycle fluctuations in demand, and that occasionally exceeds capacity. That means, over the entire analysis period, not that demand is more than the capacity, but individual cycle, because of the effect of random arrival, individual cycle, some cases capacity may be lower than the actual demand. That effect is considered. Second, also queuing due to sustained oversaturations. That means, entire period also during this analysis period, your demand may be more than the capacity. So, queuing due to sustained oversaturation during this analysis period. So, this calculation, how to calculate Q2, I have again explained to you. For your reference, this has been mentioned in slide 10 of the previous lecture E.11. So, you know how to calculate this Q2. So, this is again known, basically D2 is the incremental delay. So, the first term and the second term both are known to you now, and both I have mentioned to you earlier and we have discussed as well. Next step is actually calculation of the third term for back of the queue size Q3. Now, this Q3 accounts for the additional queuing that occurs during the analysis period because of an initial queue. My period of analysis is known. When I am starting my analysis, that time itself there is a queue. It is not that it starts with 0 queue. So, that queue effect of that queue will be also there on the overall queue and the delay. So, that is the component what is called as Q3. So, this accounts for additional queuing that occurs during the analysis period because of an initial queue when you are starting the analysis. So, this queue result is a result of the, or this queue is a result of unmet demand in the previous time period. So, maybe you have carried out some analysis or whatever operation has happened during the previous analysis period, the unmet demand that is left out from the previous analysis, that is the starting point of our present analysis period. So, that is the Q3. Now, how this Q3 can be calculated? This Q3 again can be calculated based on a few things as shown in the equation. Primarily QB, what is the QB? Initial Q at the start of the analysis period. Whatever is the Q that you take over from the previous analysis period, that is the QB, but that is there in the beginning. But then depending on this analysis period, what is the arrival rate and what is the capacity or the discharge. Based on that, two more terms may come. One is QE. QE is the Q at the end of analysis period, and QE0 that is Q at the end of the analysis period when volume is greater than equal to C and considering that QB equal to 0. Now, considering QB equal to 0 means you can interpret that QE0 does not consider the effect of or does not consider the QB component within its calculation. So, assuming that QB equal to 0, but QB actually may not be 0, right. You are actually calculating then what is the E0, Q is 0. Now, Q is 0 or QE is actually QB, whatever is the Q in the beginning of analysis period, plus T into V minus C. Suppose your whatever will be the difference, sometimes V may be greater than C, sometimes C may be V may be lower than C. So, this V minus C term could be positive, could be negative, could be 0 as well, all possible situations are there. So, the volume could be greater than capacity, volume could be less than capacity, and the volume could be equal to capacity. Accordingly, the sign will get decided. Whatever this plus may remain plus may be minus, and also this whole term may be 0 as well. So, the additional Q either it will grow or it may reduce also. If the demand is more than the capacity, then whatever is your QB value, end of the day QE will be larger than that, and if the capacity is higher than the volume, then either this whole QB will get dispersed, you will may get a 0 value of Q, or you may get a Q which is lesser than the present Q, that is QB. All possibilities are there. Now, if V is less than C, then what will happen? Capacity is higher, discharge is higher than the vehicle which is arriving during this analysis period. So, the whatever initial Q you have QB, those vehicles, some of those vehicles will get discharged. Now, if the value T you calculate like this, QB divided by C minus V, because we are assuming here C is greater than V. So, C minus V, if this value is less than capital T, the analysis period, that means what will happen? The whole QB which was there in the during the analysis beginning of the analysis period, all vehicles will get discharged, there will not be any Q, right. So, in that case, if you take this equation and put this value as T equal to QB divided by C minus V, then what will happen? This will be actually QB minus QB equal to 0. So, you started with QB, your arrival rate is lower than your capacity discharge, and T is what? Small t, duration of unmet demand in the analysis period. So, duration of unmet demand is less than the analysis period. So, if your analysis period is 15 minutes and your T is 10 minutes, then after 10 minutes there is no unmet demand. So, the Q will vanish, right. So, end of this analysis period you will not get any Q. So, this calculation is valid, it will be 0, then QB minus QB equal to 0. Now, if this duration of unmet demand in the analysis period is suppose greater than T, that yes, there is a difference, my discharge or capacity is higher than my demand. So, obviously, the QB will start reducing, whatever was that initial Q over during this analysis period, this number of vehicles will be lesser and lesser over time, but my time or the duration of unmet demand in the analysis period is higher than my analysis period. So, the whole value Q3 or QE will not be 0 in the end, but it will be lesser than the present QB value. How much will get discharged? How much will be QB minus how much? QB minus then capital T into V by C, V minus C, capital T into V minus C, but C is higher. So, it will be actually QB minus capital T into C minus V. What is the difference between C and V? Over a time period capital T, that much reduction will happen. So, QB minus that term. How to calculate this value when V is greater than equal to C? We will discuss in after 2-3 slides. We will come back to this part and discuss again. In this calculation, coming back to our calculation, and then obviously total Q is Q equal to Q1 plus Q2 plus Q3. Now, in our calculation this Q3 is 0. So, we actually omit this term or just simply put it as 0. And then I have shown you in this slide, we know the directions, we know the length group, we know the value of Q1, we know the value of D2, that delay, random delay component, the capacity, number of lanes. So, accordingly, based on our calculation here Q2 C divided by 3600 into n into D2. So, that calculation we can do, we can get the value of q 2. q 3 in the present example is 0. So, the total q will be q 1 plus q 2 plus q 3. That is the average back of q estimate for a lane group during the analysis period. Now, once you have done that, we know how much will be the value of q, and we know how much is our available q storage distance, that is an input. So, we know the average available q storage distance. So, what is then the RQ, q storage ratio? My q length is q, actual q is length is q, multiplied by LH. What is the LH? LH is average vehicle spacing in stationary queue, meter per vehicle, q is number of vehicle multiplied by meter per vehicle. So, you know the length, divided by LA. LA is the available q storage distance per lane, how many meter, all this per lane wise. So, this LA is known, LA is actually an input. So, this ratio will give you the q storage ratio. What proportion of the available q storage distance is actually getting utilized, and obviously, it should not be more than 1, right. Then that operation, existing operation, if it is creating the RQ as more than 1, then it is not acceptable. One more calculation here is given, how to calculate this LH. LH is the average vehicle spacing in stationary queue. It depends on primarily considering car and heavy vehicle. These are the two vehicle types considered in the Highway Capacity Manual 2016. So, what is the proportion of heavy vehicle? So, 1 minus 0.01 into that percentage of heavy vehicle. So, obviously, if you have 10%, then this 1 minus 0.01 into pH will be 0.9. So, 0.9, in that case 90% you have car. So, 90% car, 0.9 into LPC. What is the storage passenger car or stored passenger car length, plus 10% if you have commercial vehicle or heavy vehicle, then 0.01 into that 10%, which is 0.1, multiplied by PHV. PHV is the that PHV into 0.01 is 10% multiplied by the length of average length of heavy vehicle. So, accordingly you can calculate the average vehicle spacing in the stationary queue, considering the effect of car and heavy vehicle as per there, at what proportion they are shared, they are sharing in the they share in the overall traffic stream. Accordingly, you can calculate this one. So, here we have calculated, now all the values are known. I have shown you here how for the eastbound through lane group, how we can calculate this value. So, we know that this average length is taken as 7.5 meter for the stored passenger car, stored heavy vehicle length 13.5 meter, and you have 10% actually this heavy vehicle. So, 90% will be the cars. So, 7.5 into this value plus 0.1 into 13.5. So, you get that 8.1, that is way we can calculate. Now, accordingly that is the this is the LH value. So, you can calculate LH, and once you know the LH value, you can calculate this Q storage ratio, and in this case it will be 8.1 into 3.8 divided by 60. So, only 0.52. So, like that you calculate for every lane group. Here interestingly you can see one value is 1, that means just where the whole Q storage distance is actually getting utilized. So, little bit higher means it will not no more be acceptable. In fact, we should not operate with this Q storage ratio as 1, because marginal increase means it will fail in that sense. So, now a quick interpretation of the results, how we can interpret the results. Now, let us consider a scenario where for the overall intersection volume to capacity ratio is less than 1, and for all lane groups or every lane group xi, I indicates a lane group, for all or individual xi also it is less than 1. There is no problem, then everything is fine, the whole intersection is operating nicely. Of course, we have to see if this xi and xc all less than 1, but it should not be too much on a lower side, that also we need to check. But as long as it is lower than 1 and maybe 0.8, 0.9 in that range, it should be quite acceptable. So, at least the capacity wise there is no issue. So, whatever may be the xc and xi, as long as they are all less than 1, that clearly indicates that there is no capacity deficiency in the lane group. Now, take that another scenario, x is less than equal to 1. So, overall intersection capacity wise it is fine, but some lane groups or for some lane groups xi is greater than 1. What does it indicate? The overall operation, overall intersection looks all right, it can handle, but the green time distribution is not proper, because some cases xi greater than 1, some other cases greater than less than 1, maybe some cases significantly less than 1. So, that indicates the green time allocation for different lane group needs to be adjusted further, right. So, the indication is cycle time is generally not appropriately allocated among the phases, and therefore, reallocation of cycle time should be considered, so that additional green time is given to the phases serving the lane groups with xi greater than 1. So, where volume to capacity ratio for certain lane group is more than 1, we should allocate more green time there and reduce the green time for the other lane groups or other phases. Now, another possible scenario, probably the worst, could be x is greater than 1 and some or all xi also greater than 1. So, you have now problem with the overall intersection capacity and a few or all individual lane group capacity. That is a real problem. So, overall signal timings and geometric design, the present one, the present signal timing and the present geometric design is unable to provide adequate capacity for the given demand flow. So, you have to think something more, not simply reallocation of green time to different phases or different critical lane group. You have to think something more than that, because the overall intersection capacity is also not adequate. So, some of the suggested improvements may include change in intersection geometry, that means change in the number or use of lane. So, you know that critical value for lane group, it is going more than 1. So, in that case, if you add additional lane, obviously it will benefit, that will give benefit to this overall calculation of xi. So, that is one possibility, or use of lane, the way the present lanes are utilized for through left turning, right turning, shared, exclusive, whatever the things, some further changes there to bring down this overall xi values lower than 1 and also the xc less than 1. and change of course in signal phase sequence or timings as appropriate, along with the changes in additional lane or use of lane, overall changes whatever will happen. So, you have to think of signal phase sequence or timings, all are may be changed. Signal phase sequence or timings may also be changed. So, these are the possible scenarios and what actions if at all is required. Suppose first case no action, everything is fine. Second case yes, reallocation of the green time. Third case it is not only reallocation of green time, but change the number of lane, use of lane, increase the cycle length if it is determined to be too short, and also change the signal sequence or phase sequence or timings. Multiple interventions may be required. Now, if I have to summarize the results which we got based on our example problems, then what you see here, all these calculations have been done earlier, but now I am trying to relook at the results. You see the V by C ratio 0.579, 0.611, quite on a low side, but you also have values like 0.996, 0.924, quite high, acceptable, not more than 1, but near 1. So, even some slight fluctuations in the demand may cause this V by C ratio to be more than 1. Also, if you see the Q storage ratio, in all other cases it is quite acceptable, but for westbound through and left shared lane it is 1. That means, a slight change in the demand for this lane group will cause your RQ, the Q storage ratio, to be more than 1. So, what it is saying? And if you see the overall intersection 0.891, quite happy situation in that way, right. Not too low, not very close to 1, it is reasonable, right. In an almost I will say yes, that kind of values may be accepted quite comfortably. So, intersection as a whole operates at a high V by C ratio, not too close to 1, not too on the lower side, not like overall is 0.4, 0.5 or 0.6, not even that. But it is recommended that capacity for all critical groups be increased, because you can see especially this westbound through and left. So, that is what I have said, that all lane groups should be increased and that the green be allocated to provide more balanced V by C ratio in all the lane groups. Ideally, we do not want values to vary so much, 0.579 in some case one lane group and 0.996 in another lane group. So, it indicates some reallocation of the green time probably will benefit the operation of traffic at this signal. And as I said, the RQ ratio, RQ value, the ratio of storage ratio, it is again for westbound through and left shared lane, this one you can see here it is 1. Okay. So, westbound through and left you can see here 0.996, this V by C ratio is also critical, and here the RQ value storage ratio is also 1. So, it indicates that with little increase in the flow will result in more queued vehicles and may block vehicles from moving forward, right, because the upstream discharge also may get affected. So, it may be a real problem. So, a reallocation of green time to make more balance in terms of the V by C ratio and more rational distribution of the Q storage ratio would actually be possible, and that will benefit the operation of traffic in this intersection. But the overall utilization, overall volume to capacity ratio for the intersection should be generally acceptable. Now, Coming back to little bit more analysis and more discussion about the initial Q delay. We talked about the Qs, but then initial Q delay. This part we have not discussed in details. So, little bit more discussion about the initial Q delay. Initial Q delay means when we are starting our analysis or in the beginning of our analysis period, there is already a Q and that is shown here as Q b. So, you are starting your analysis period here, here your capital T is the duration of analysis period. So, here it is 0 and here it is t if I consider this time axis, of course, capital T the analysis period. So, in the beginning of analysis period also only you have a value of Q b. So, this is the cumulative arrival. So, cumulative vehicle already Q b number of vehicles are there. You have to take that right from the beginning, from the previous analysis period. Now, although this Q b remains same in different cases, but then the other things there are based on the arrival and based on the departure, there are three possible scenarios which are shown here. First, the simplest one and the most comfortable one. What is there? You can see the red line is showing the arrival, cumulative arrival, and this dotted line showing the cumulative departure. So, obviously, since there is a Q b number of vehicle, D 3 is the delay, additional delay, right, because these Q b vehicles need to be discharged. So, when all these Q b vehicles will get discharged after D 3 time, D 3 seconds. So, D 3 is the additional delay in this case. So, D 3 is the additional delay in this case. Now, you are seeing interestingly the cumulative arrival and cumulative departure, they are meeting at this point, and they are meeting at this point at what time? At time small t from the beginning of the analysis period, and this small t time is lesser than the analysis period capital T. So, within the analysis period, my considering the Q in the beginning, my cumulative arrival Q b plus my whatever vehicles are arriving during this analysis period of small t seconds, I am able to clear all the vehicles within small t seconds, and small t is less than the overall analysis period. So, end of the analysis period what will happen? Your Q length will be 0, all vehicles got cleared. So, you are starting with a Q in the beginning of analysis period which is Q b, but end of the analysis period you will have 0 Q, no Q. So, T is the small t is the adjusted duration of unmet demand. So, unmet demand is served entirely 100% within this analysis period small t, which is also lesser than capital T, the overall analysis period. The second one is not such a happy situation, somewhat different. Here again we start with Q b. So, obviously, there will be delay, but the arrival and the departure rate during this analysis period is such that they are not meeting, but also not that they are simply parallel. Parallel means they are not going to meet now, right, or as in the case 3, this one, there the gap is widening further over the analysis period. You can see here, this is the arrival and this is the dotted line is the departure, and the red line is shown here which is parallel to the departure, right. So, here in this case the arrival line actually is on the left side of this red line, which is v equal to c, and here the arrival, although I have shown it using the red line, but this arrival line is somewhere like on the right side of the line, where arrival is equal to the departure. So, exactly not parallel. So, if you take the width of or the length of this line, this solid line, and the length of this dotted line, both are horizontal lines, the dotted line length is lesser than the length of the solid line. That means, what will happen? Your arrival, whatever is your arrival rate, your departure rate is higher than that. In this case also departure was higher, but the difference was such that the arrival and departure rates were such that the departure cumulative departure curve could catch up with the cumulative arrival within this analysis period, but here no. Within the analysis period, the cumulative departure curve should not catch up with the cumulative arrival curve, considering also the q which were there in the beginning. So, what will happen in this case? After the analysis period, it will not be 0 like the first case, but it will be not same as QB or will not even increase further. It will be something lesser than QB, because during this whole analysis period capital T, the number of the queued vehicles, the number will get reduced. All these vehicles, so whatever will arrive, the rate is such that, suppose there is, so it is the gap is getting reduced in this case. Now, go to this extreme situation, where the arrival rate during this whole analysis period T is higher and significantly higher. So, forget about this QB, with this arrival rate itself, all the vehicles which are arriving during this analysis period cannot be cleared, because it is even at higher rate than the departure. Arrival rate is even higher than departure. So, here there will be two effects. The QB will be there, that length will be there, plus due to oversaturation during this analysis period, there will be additional Q. So, first case QB after the analysis period becomes 0. Second case QB does not become 0, but get reduced end of the analysis period, and Q3 is the worst. It will be QB plus something. What is the plus value? Is this one after this analysis period. So, the end of this analysis period, whatever Q you will get, that Q length will be higher than QB in this case. Here during the after this analysis period, your Q length will be lesser than QB, but not 0. In this case, it will be 0. Now, with this we can calculate what is the D3. There is a formula, it is a quadratic equation. You can use this formula to get the value of D3, and in this case QE, I have mentioned it earlier, is QB plus T into V minus C. I have explained that if it is V is less than C, then T will be can be calculated like this, and if the T is less than capital T, that is small t is less than capital T, then you use this small t in this equation here, Q equal to QB plus T into V minus C. if this t becomes more than capital T, then you assume the small t as value equal to capital T, then put it there. So, what will happen in that case? V less than C. So, C is higher. So, this will become negative, that means Q B minus in the overall analysis period capital T, how much is the difference between V and C. So, essentially if you take minus, it will be then C minus B. So, the Q B equal to Q E will be Q B minus something, Q length will get reduced. What will happen if V is greater than C? Further addition, right. So, whenever there is an oversaturation, then this small t will be equal to capital T. And what will be your Q E 0? Q E 0 will be T, this equation small t gets replaced by capital T into V minus C. Okay. So, that will be the value of Q 0. And what is Q 0? I have told you earlier. Let me go back again and tell you. What is Q E 0? It is the Q at the end of analysis period when V is greater than equal to C, and Q is Q at the end of the analysis period. So, coming back, what we can say now? We know conceptually the possibilities, how to calculate also, the formula is also known, the equations are given. So, it is a simple calculation now. So, let us consider whatever we have taken the worst, that westbound through and left lane group. There the capacity is 531 TPC per hour and our actual demand flow rate was 529. So, it was almost like 1.996 or something we got. Now, suppose if instead of 529, if it would have been 551, then what will happen? Capacity is 531, actual demand flow rate is 551, and if we consider 4 consecutive 15 minutes analysis periods separate, one 15 minute, then 15 minute, again 15 minute and the fourth 15 minute. So, if we consider 4 consecutive 15 minute or 0.25 hour analysis period, then what will happen? There will not be any Q, initial Q in the beginning of first 15 minute interval. But then since V is greater than C, there will be Q at the end of the first 15 minute interval, and therefore, at the beginning of the second 15 minute interval and eventually in the beginning of third 15 minute or fourth 15 minute interval, there will always be a QB value. What will be the calculation in that case? So, we are considering a every time 4 consecutive analysis period each of 15 minute or 0.25 hour, and this is all 551. We have assumed that. I say that what will happen if instead of 529, if the actual demand flow rate is 551. So, in that case what will happen? This V is 551, capacity is 531. In the beginning of your analysis period you have 0, but then Q E 0 as per the calculation you will be 5 and then Q E will be what? Q B plus Q E 0. So, total will be 5. Now, this 5 will be actually Q B for the next analysis period. Again you calculate what will be the Q E 0 in this case. It will be 5, and as I said, this Q E 0 says when V is greater than C and with QB equal to 0 does not mean that it will be only applicable when QB equal to 0. This tells you that assuming that QB as 0, that means QB effect is not included in the calculation of Q is 0, that is the meaning. So, what will be the actual QE? Then it will be QB plus Q is 0. So, you get 10. Now, 10 will come here, again you will find Q is 0 is 5. So, what will be QE? QE will be Q is 0, because in E 0 Q is 0 calculation we are not adding this QB. So, actual Q at the end of analysis period will be whatever was the QB plus, because this is oversaturation, what is the additional Q during this analysis period due to oversaturation. So, the total Q will be QE at the end of analysis period will be QB plus Q is 0. So, you can see here if there is a little bit of increase, then there will be 20 vehicles TPC per lane at the end of the fourth period. So, this may be a concern, because then your Q storage ratio will be higher and higher, and depending on the situation it may even block the upstream signal, or even if it does not block, it will influence the operation of upstream signal very significantly. So, before we close, last part is basically the pedestrian delay or signal requirement, not pedestrian delay, but pedestrian, last part is pedestrian signal requirement. So far in all our calculation, planning level analysis, operational level analysis, we have not considered or discussed this part. Since this is operational analysis, let us touch this part also, very simple. If there is an existing, if in existing intersection, if in an existing intersection there is a requirement and you have given already the pedestrian green, because pedestrians want to move and that is the facility you want them to use at grade facility with the signal control for pedestrians, then how we judge whether the green time given is adequate or not? There are two considerations. One, the first one, the time a pedestrian needs to perceive the signal indication and traverse the crosswalk. They have to cross the road. So, what is that length? So, here you can say this is the minimum time required. We are not considering the pedestrian volume here. Suppose one person, but that one person has to cross the road safely. So, what is that minimum time required? That is one criteria. So, GP min is actually TPR, it is perception reaction, as we normally use for vehicular traffic. For pedestrian traffic also there is a perception reaction. So, pedestrian perception of signal indication and car departure time, and this is taken as 7 seconds, and this is taken as 7 seconds as per Highway Capacity Manual 2016. Of course, this value could be even lower, could also be higher depending on the context, what is the type of pedestrian and different other conditions. Plus, so this is the time anyhow required, plus pedestrian has to cross. So, what is the value of LCC? LCC is nothing but car to car crossing distance divided by what is the speed, pedestrian walking speed. So, LCC by SP minus yellow time or amber time minus the all red time. Because we are doing this minus y minus r, because we are talking about the minimum required time. Obviously, ideally it should be little higher. So, this is the one component or one criteria that we need to check. So, our available green time must satisfy this criteria. Second, based on the volume of pedestrians and also how much width we are providing. This is the width of the zebra crossing, where people are crossing actually the road. So, if it is greater than 3 meter, then it is 3.2, 3.2 here again is the perception reaction part, which was taken here as 7 seconds or could be higher, could be lower. What was the TPR? In the second criteria, it is taken as 3.2 seconds plus as usual LCC, curb to curb distance divided by the pedestrian walking speed, whatever you take, plus now the number of pedestrians NPD divided by WE, and this formula is valid, equation is valid when the width of the crosswalk is greater than 3 meter into 2.7. So, per feet or per meter, whatever way we take per feet, then multiplied by 2.7. If the width of the crosswalk is less than equal to 3 meter, then more or less the same equation, except that this divided by WE that we are not doing. So, it is 0.27 instead of 2.7, there is a difference that way. So, 3.2 remains same, LCC by SP it remains same, and here it was 2.7 into NPD divided by WE. Here we are taking 2.7 instead of that, we are taking 0.27 into NPD, right. So, that is the equation. How we can get the NPD? NPD is the number of pedestrian crossing during an interval, that is a particular cycle. So, how many pedestrians are being processed or need to be handled per cycle. How you get that? How much pedestrians are crossing the road? What is the hourly flow rate? Divided by 3600 multiplied by the cycle time. So, that many pedestrian have to cross this particular place or for this particular travel direction in every cycle. So, that is the way you do it. So, if I have to summarize, I will say today we discussed about how to determine the queue storage ratio, how to interpret the results, a further understanding possible scenarios and how to calculate the initial queue delay, and also little bit mentioned to you briefly about the pedestrian signal requirements, how the existing operation, existing signal, the given green time for the pedestrians, how that can be judged, the adequacy of that can be judged. So, with this I close this week 2 also, and thank you so much.